Excuse me, but I think you're muted.
Okay, that right. Huh. Yeah. Right. So what I was saying was that we're going to go through the first 3 pages, and that I'm going to start by recapping the information from the slides. All right. So yeah, a critical number is a value um, for x such that the derivative at that value is equal to 0, or it is undefined. So really, we're talking about the values that make the derivative function undefined. That's why when the the usual process for this kind of thing is to take the derivative and then set equals 0 and solve. That'll give you some of the critical numbers, and usually it'll give you most of them. But there are some more that can crop up that come from the derivative being undefined there. And so you need to check both conditions. And I think there's at least one problem in the homework where one of the critical numbers that is rather important shows up from just getting the derivative to be undefined. Okay, so after you have critical numbers, the next thing is that you normally would do some kind of a number line where you then mark the critical numbers. And that lets you see more clearly the intervals that you need to test. Test to meaning like you determine like, is the function positive or is it negative on that interval? And we'll see examples of that. I think also I'll want to explain the first derivative test and the second derivative test. So first derivative test. Well, it boils down to just two conditions. So let's say you've got like the derivative there, and that this is going from plus to minus. So this means you have a local max versus if your first derivative is going from minus to plus, that means you have a local min. And the way that I would go about like visualizing this is kind of like you can sort of draw something on top here. So derivative being positive means that the slope is increasing, and then negative means it's decreasing. So that's why this guy looks like a local max, whereas this one looks like a local min. So that's the contours of the first derivative test, essentially. So if there's any other like signs like plus plus or minus minus, that is inconclusive. You can't tell if the value here is like a local min or max. In fact, it probably shouldn't be. So yeah. Right. And so that's first derivative test. Now let's do second derivative test. So second derivative test is a little bit more nuanced in a sense. Like it doesn't have to do with these sketches. Instead, what it has to do with is you plugging into the second derivative. So suppose you have a critical number, I guess we can say let A be a critical number. Such that on the derivative, it's equal to 0. So what this is meaning is like, because in the definition of a critical number, either you could have that critical number is a place where the derivative is 0, or it's a place where the derivative is undefined. We are actually only interested in the ones where the derivative is undefined for those. So you kind of want to like isolate or filter that list of critical numbers out to just the ones where it's undefined. And then second derivative test says you can use those critical numbers and plug into the second derivative. And that tells you something called concavity. the way that the function curves. Okay, so you then plug those critical numbers into the second derivative. So if you let's do it like this. So if you plug it into the second derivative and you get a positive, that means concave up, which pictorially looks like this. If you plug into the second derivative and you get something that is negative, that means concave down, which means that you get a picture that looks like that. And that's how you would then tell local min or max. So concave up means local min. Concave down means local max. Okay, so I'm sort of doing a chain of reasoning, but in order to conclude, like really the ultimate conclusion you're supposed to make is the one where like first you plug in, and then from that you get to the fact that you get a local min. Like that's what the statement of second derivative test is going to say. If you just like, I think, read the slides or read a textbook, it's just going to be, oh, you plug it in, you get something that's positive, then what you have is local min. But the real reason why is actually because like we have this intermediate notion of concavity in this picture. So that's kind of the way that you should go about remembering this. Okay, so now just to recap, right? First derivative test, we only used the first derivative, and from that information in the first derivative, we can conclude that like this particular place where there's a critical number, that is either a local min or a local max. First derivative test tells you that. Second derivative test tells you exactly the same information. It just uses the second derivative instead of the first derivative. With the first derivative, you test values that are around the critical number, and you look at like the change in signs. With the second derivative test, you plug in at that number, but you plug it into the second derivative, and you check, and the sign will tell you like whether it's a local min or max. So these two tests are just two different ways to figure out the same information, but we tell you both of them because in some circumstances it's easier to do one than the other. And I'll say that usually it's easier to do the first derivative test, since usually the second derivative is harder to calculate. But there are instances where the second derivative is very easy to calculate and also very easy to plug into. So like, I suppose like you might see that in the homework. I don't remember, but yeah, occasionally you can use the second derivative. All right. Let's see, is there anything else I need to explain before we start working? I think that should be everything. Okay. Any questions? No? Okay. All right. Then let's go ahead and do some problems. All right. So we have a profit function, and we want to figure out when is the profit increasing and decreasing, and we want to maximize the total profit. So increasing, decreasing, once you hear those words, you should start thinking, like you should immediately think first derivative. I'm going to use the first derivative. And so let's go ahead and calculate the first derivative. So that should be straightforward. 200x plus 10200x. Oh, no, no x. Doesn't let me erase. That's weird. Okay. Okay. And so the usual process is that we set this equal to 0 and solve in order to find the critical numbers, which we then draw on a number line. Okay, so we set this guy equal to 0 and we solve. When we solve, bring the x to the other side. 10200 is going to equal 200x, and then we could just cancel off the 100, and also then we divide by 2 so that we get 51. Okay, so x is 51 is going to make this first derivative equal to 0. Hence, it's a critical number. And what I do normally is I label my number line, and I put tick marks at the special locations at the critical numbers when the derivative is equal to 0, when it is undefined. And the reason I do that is because the tick marks actually separate out the regions of the number line that have like the same sign. So the sign changes only happen at the tick marks. Okay, so now we can think, what happens in this region? Is it positive or negative? So I then look at the function. So I look at this function and I think about like, yeah, when is it, what's going to happen to it? So if we were to plug in a number that's greater than, if we were to plug in a number that's greater than 51, then what you should notice is that the this term here, the minus 200x, is going to dominate over the 10,200. And so this is actually going to be negative in this region. And then similar reasoning is going to give you that this side is positive. Or you could just choose an easy number. In this case, there is an easy number here, which is just 0. You just choose 0 and you see that the first derivative is positive. So these signs then tell you whether that interval is increasing or decreasing. So we can then just label the intervals. So increasing is going to be from, well, minus infinity, I guess. We can say minus infinity. The pen isn't working today. Funny. And decreasing is going to be from 51 to infinity. I mean, there are some realistic bounds on this that you could place. Like you could say that like the pricing is not going to be negative, but we're just going to do the naive thing here. I just write it like that. I think. All right. So right now to conclude this thing about maximizing total profit, it's really annoying that I can't see my cursor so well. So yeah, maximizing total profit. You can see that in this, like there's a local max that's 51. And something else will say like that this is actually a global max because there are no other sign changes. So this will be actually the global max for the local function, just due to that fact that it's the only sign change. But we can just say it'll, we can be a bit more vague about it, I think. So to maximize, what do we use the word choose here? Maybe I said should charge, yeah. Should charge $51 per pair. Okay. Number 2 starts off pretty much the same. Okay, so finding critical numbers. Again, what we do is we take the derivative, set equal to 0. So the derivative is going to be 110x to the 10 minus 110x to the 9, which we would set equal to 0. You can divide the 110. Well, it's probably better to factor instead, just to make sure we don't just arbitrarily get rid of information. So 110 x to the 9 and then x minus 1. Okay. So this guy is set equal to 0. So our critical numbers are x equals 0 and 1. And you can check like, yeah, it's defined everywhere. So this one is not the problem where that matters. I think that's the next one. Yeah, it is the next one. All right. So, okay, we found the critical numbers. Next, where is it increasing? Where is it decreasing? Well, again, to determine that, I would draw a number line, marking my critical numbers on the number line. And then we look at this function, the derivative function. So I will look at it in factored form because it's easier to reason about. And then you can like consider the interval. So the usual way that people teach you this is they'll tell you to choose a number and to plug in there. That's the long way to do it, but that will work. So like if you are very confused about, I guess, the more abstract approach, that I'm going to try to tell you to do, then by all means go ahead and do the whole plugging in kind of thing. And I think even for like for the third problem, I basically had to resort to plugging in because it's hard to analyze, or at least it was hard for me to analyze it like last night. But for this one, it's easy to analyze, is what I want to say. So let me switch over to a pointing thing. So notice that like we have this in factored form. So this is really nice because you can kind of just tell like, is this chunk going to be positive or negative in in whichever region that you're trying to concentrate on. So the trick that I do is I always start from the right because usually that's the easiest thing to compute. Usually everything is going to be positive. Notice here, like if I start over in this region where things are greater than 1, where x is greater than 1, this x to the 9th is positive, this x minus 1 is positive, the whole function is positive. So I can easily say that this part is positive. The next rule I need to tell you is what happens or how I consider like regions that are to the left. So I basically start at the right and I go to the left successively. And each time that I transition over one of these tick marks, that is only going to change one of the signs in the factored form of the first derivative. So if I transition over from x is greater than 1 to x is less than 1, but greater than 0. So from this region to this region, only this factor is going to change in sign. This is going to turn from positive to negative. And so I only need to track one difference in signs, and then I can consider like, does that affect the whole derivative or not? So I can actually very quickly fill out like this sign chart, as it's called. So this going from here to here, this guy changes, and that's going to change the sign of the whole q prime. So negative. Okay. And then similarly, going from this region between 0 and 1 to the region below 0, that's only going to affect the sign of the x to the 9th, or the x inside raising to the 9th. And so that raising to the 9th is actually going to maintain the sign, which means it's going to flip the overall sign of the function. So, so that means that this actually turns into a plus, this region here. So when you think about it in this way, the thing to concentrate on ends up actually being the power that you're raising the factor to. So if instead of this being x to the 9th, this was x to the 8th or x to some even power, that would actually get rid of the change in sign that would happen, right? Like that this inner term x would go from being positive to being negative, but raising it to an even power would get rid of that flip of sign, which would mean that the overall sign of the function q prime would not change. So I'm saying this in a really I'm trying to say this very carefully because I know that this is something that I try to teach my students and usually takes them a while to get comfortable with. It's a shortcut, I'll say. I'm telling you guys a shortcut. It doesn't feel like a shortcut right now, but it will if you ever get to like easy looking problems that have a lot of factors. Doing it like this is a lot faster than picking a number and trying to plug in. It's the idea is to analyze the structure of the function and determine an easy way to calculate just using pluses and minuses instead of actual numbers. So, but you can also try to construct like such an approach on your own, and you'll eventually arrive at the approach that I have been trying to tell you. Okay. Anyway, we have the sign chart filled out. That's the important thing. Okay. From that, we just read off the increasing and decreasing information. So increasing is first the derivative being positive. So let's say increasing, that's going to be from minus infinity to 0, and also from 1 to infinity. Decreasing is going to be from 0 to 1. Okay. Yeah. Next, we have using the first derivative test. So remember that the first derivative test is about transitions. So plus to minus, minus to plus, what do those actually mean? And so this one increasing to decreasing, maybe I'll just draw the schematic picture on top. So it kind of looks like that. All right. So local min, local max. I didn't write the full coordinate. I just said like the x values. So the local min happens at x equals 1. The local max happens at x equals 0. If you wanted to, you could figure out the full coordinate. I don't really think that the problem is asking you to do that here. But if you wanted to figure it out, you'd have to plug it into the original function. You'd have to plug it into this p, which is going to have some thousands to work with. Okay. All right. Any questions so far? Okay. All right. Number 3. So this problem is actually a little tricky. Just a little bit. So the derivative, well, that's straightforward, right? So divide by 3 times 2, that's going to be 6x, and then it'll be to the minus 1/3 power minus 3. And we would want to set this equal to 0 and solve. Okay, well, so you'll end up with 1 over, you'll end up with a, how should I write this? Should I write it like that? I add the 3 over, I divide by 6, so I'm going to get 1/2. And you would have an x to the negative 1/3 power, which is a cube root in the denominator. You then have to reciprocate both sides, take and then cube both sides. So you end up with x is equal to 8. Okay, but this is where that thing about being undefined is important, because there's actually another critical number. And if you only wrote this, you would technically be wrong, right? So this is where I would actually prefer to rewrite this function without the negative exponent. So I'll put it in the denominator. So we have 6, and then we have a cube root of x minus 3. And now when you see it in this format, you can easily recognize, like, when is this thing undefined? Right? That's when x is equal to 0, because that would be a division by 0. So for critical numbers, I don't know if he abbreviates it in any particular way. Critical numbers, they're going to be 0 and 8. Okay. And so, right, now we use the first derivative test, which basically means we need that number line sketch. So we go ahead and try to construct that. The 0 and the 8. Okay. But so notice, like, this function is not, like, it's not in a factored form, not really. So this is why, like, for this function in particular, you kind of have to resort to plugging actual values in, as annoying as that is. So let's see. Well, maybe we can, I guess I still need a pointer. Maybe we can reason about, to me, like, the easiest number to plug in is 1, because it's over here and I can easily take the cube root of it. So if I plug 1 in, I'm going to end up with a positive number. I'm going to get 3, I think. Yeah. Okay, and then what happens if we plug in some number over here? Well, this is maybe where I would kind of shortcut it and not actually choose a number. I guess the first number that you could choose that would be useful would be 27, because the cube root of that is 3. So you get -1, fine. But another way of thinking about it is that 8 is the special value that, like, according to this calculation, it is the value that made this whole expression equal to 0. And you can check that. You take the cube root of 8, you get 2, you get 3 minus 3, so you get 0. Right. So the thing is that, like, by having 8 here, you end up with some fraction. If you increase the denominator, you're going to make this 6 divided by expression, this little sub-expression, you're going to make that smaller. So originally it was equal to 3. You're going to end up making that smaller. So you're going to end up making the whole thing negative. And you could reason that without actually picking a number, is what I'm trying to say. Okay, great. Now, over on this side, well, you've got negative values. This is where I guess I have to remind you guys that you can cube root a negative number and you end up with a negative number, like because well, -2 cubed is going to be -8. So the cube root of -8 is -2, for example. But yeah, overall, where's my pointer? There we go. Okay, so yeah, overall, like if you plug a negative number into a cube root, you're just going to get a negative number out. So this whole this fraction ends up evaluating to be something negative. You get negative minus a number, so you still get negative. So this side is negative. So you're able to reason out this whole sign chart, and then you're able to yeah, you're able to then you're able to use the first derivative test now. So minus to plus and plus to minus. So right, local min at x equals local max at x equals. So minus to plus, I'm tracing it on the screen. It's a min. And then plus to minus is a max. Okay. All right. Any questions on this problem? No? Okay. Right. Then 4 isn't well, 4 is tricky in another way. So it's tricky because now in this problem we actually have like infinitely many critical numbers, because this is a trick. This is a it's sort of a trigonometric function. It's oscillating infinitely. It's the sum of sines and cosines. It's gonna end up being oscillating infinitely. All right, so let's go ahead and do the same process though. That because we still need to do that. We still need to take the derivative, set equal to 0, and solve. All right, so here we're going to get cosine minus sine, and we would set this guy equal to 0. So that tells me that the function sine should equal the function cosine. And so now this is where we're testing your trig knowledge. All right, well, maybe I can ask you guys, what are, you can probably answer some of the x values. Don't need to answer all of them. Well, anybody? No idea. Okay. So there should be at least one value that pops to mind, which is 45-degree angle, because you should know that sine and cosine on a 45-degree angle are both going to be √2/2. So that's the value that should come to mind, which is around here. So that's pi/4. And then from that, you should then say, oh, you can tack on a 2 pi k to that, because revolutions around the circle are still going to get you to the same angle, and so the trig functions will be equal on that. And then the other one is on the opposite end, over here. Right. So, like normally you might think like, what about the other two quadrants? Well, the thing is that one of the functions will be positive, the other will be negative. Whereas like on this third quadrant, or no, not third, second, no, third, yeah, no, it is third. On the third quadrant, sine and cosine are both negative. So this guy over here also ends up being in the set of critical numbers. So this is 5 pi/4. Okay, so you have these two families of critical numbers. Okay. So yeah, analyzing this is be a tiny bit tricky. So we have to find local mins and maxes. Easiest way to think about that is to do the number line again. But here we might need to extend this quite a bit because we want to see some periodicity. We want to make sure we extend far enough that we see the pattern. Pi over 4, then 5 pi over 4. And then the next thing that'll happen, so we're wrapping around the circle. So we end up over here. The next point that we're going to get is going to be a version of pi over 4. So we just have to add to that 5, 7, 9. So it'll be 9 pi over 4. And if I wanted to, I could probably extend that a little bit more, but I'm also going to come down on this end. So pi over 4 minus 1 minus 3. So minus 3 pi over 4 you can check is in this family of 5 pi over 4. Just plug k is minus 1, I think. Yeah. All right. Right. Then the next thing is to probably use some useful values, plug useful values into h prime, since in this case, it's kind of hard to analyze this otherwise. We kind of actually need values in this case. So, well, if I talk about this region between negative pi over 4 and pi over 4, 0 is the easy value that comes to mind. So let's, maybe I'll just put some scratch work up to the somewhere. So we're plugging 0 into the first derivative, and cosine is going to be 1, sine is going to be 0. So I get 1, I get positive. Okay. Between pi over 4 and 5 pi over 4, let's just look at it in the picture. So a nice value that we could use pi, or we could use pi over 2. Either of them would work. Maybe I'll just use pi. Okay. So with pi, we're on the y-axis. We're on the negative end. So that's going to tell me that cosine gives me a minus 1 and sine gives me a 0. So we end up with a negative here. Okay. And now let's think about this region between 5 pi over 4 and 9 pi over 4. So that is just any angle around here. So I can actually just use the angle 2 pi. In which case cosine is going to be 1, sine is going to be 0. So that's good. We get plus for this. And you can kind of guess by now that like this is going to oscillate back and forth. Like you can get plus and minus and plus and minus. Like it'll just continue on and on. Maybe put some dotted just to indicate that. And so what you see here is the pi over 4 and the 9 pi over 4. They belong to the same family. They belong to this first family. And you see going from plus to minus in both of them. Oh, yeah. So you're going to be able to classify this whole family as being a local max in this case. And then the 5 pi over 4 and the minus 3 pi over 4 also belong to the same infinite family. It's going to belong to the second family, and they're both minus the plus. So they're both, so the whole infinite family is going to correspond to local mins. Okay. And so we can just write that. So what did I say? Local maxes are x is equal to pi over 4 plus 2 pi k. And the local mins are going to be x is equal to 5 pi over 4 plus 2 pi k. Okay. And then, so C is a little, which I didn't think about how you want to show this rigorously. Plus 2 pi k isn't gonna evaluate something different. Okay, yeah, I guess so. Yeah, because in order to reason about this, like intuition should tell you that these pointer again, that these values should actually be the global maxes and mins. Intuition should tell you like this is going to also be a sinusoidal function. It's going to go up and down, just like how sine and cosine go up and down. It just might be distorted in a little bit, but it shouldn't be too terrible. And you can actually check that by just graphing it on a graphing calculator like Desmos. And you'll see that that conclusion is exactly right. But to be rigorous about this, you might want to actually consider how would you plug into this function. And so I was just thinking about that just now, and I figured out that like actually the 2 pi k will disappear when you're plugging in because the sine and cosine functions are periodic there, and like when you tack on a 2 pi k, that does nothing to the function. It doesn't change the value of the function at all. So maybe like maybe as like scratch work, what you might do is is it actually called h? Yeah, it's called h. Okay, you might actually plug in h of, and then you say like pi over 4 plus 2 pi k. This guy is actually equal to h of just pi over 4. And then what is that? Well, sine is going to be root 2 over 2. Cosine is going to be root 2 over 2. You're just going to have 2 copies of root 2 over 2. So you just get root 2. And similarly, if you want to plug in, what was it, 5 pi over 4 plus 2 pi k. Well, again, the wrapping around the circle isn't going to change the value of the functions. So that's just going to reduce to h of 5 pi over 4. And on that side of the unit circle, we're on the third quadrant now, sine and cosine will both be negative, and they're going to give you negative root 2 over 2. So you get 2 copies, and so you get negative root 2 in total. Okay, and so that's kind of the way that you would argue that. Does it have globals? Yes. I would rather like abbreviate this and say like the locals are the globals, but maybe it's better in this case just to like copy it down. Maxes. Yeah, pi over 4 plus 2 pi k, and global mins at x is equal to 5 pi over 4 plus 2 pi k. Yeah. All right. I mean, without this evaluation or these two evaluations, technically, you would only be running on intuition, and there are ways where you can just tack on a couple of sines and cosines, scale them up and down a little bit, and you'll get complicated looking wavy patterns where you'll have local mins that are not global. So yeah, it's better to actually do this check, I would say. Okay. Any questions? All right, no. Okay, so I'm gonna have to maybe go quite a bit faster, or I'll only do most of 6, not all of it. We'll see. All right, so number 5. Oh, this is just interpreting stuff. Okay, so we have population is increasing, the rate of population growth is slowing. So you just convert those two statements into mathematically what it's actually saying here. So that the first thing, the population is increasing, that tells you that the derivative is something. It's positive, right? So it's greater than 0, which means that it's positive. And the rate of population growth is slowing. If you untangle what that statement is saying, population growth is the derivative. The rate of it growing is slowing down. That's a statement about the second derivative. And it's saying that it's actually slowing down, so the sign is negative. It's less than 0. Okay. All right. So now number 6. Right. So this function does not look appealing, but yeah, we just have to take the derivative, and that's why it does not look appealing. So we have to do a quotient rule. And at this point, yeah, basically, because you're trying to do something with this, you're gonna have to clean it up a little bit, because we have to set this guy equal to 0 and solve it somehow. What I can do is I can pull the e to the x out, and I see that we've got a minus x and an x. So you just have a, wait, you don't have an x, you have a 1. That's my bad. I get not, it's gonna be hard to target that. Okay. Yeah, times a 1. Because it's the derivative of that. So you have a 1 and a minus 1, so you have an x times e to the x on top, and then x plus 1 squared. And you're setting this equal to 0, or you're determining when is it undefined. So setting equal to 0, though, one thing to notice is the denominator is always going to be positive, or 0. That's the other condition. But yeah, so that's not what matters. The numerator is what matters for setting this guy equal to 0. And e to the x is never going to equal 0. It's always positive. So x is 0 is what you would get from this. The or undefined is going to give you x is equal to -1. So the critical numbers are x equals -1 and 0. Okay, my computer's lagging. That's a bit funny. All right. Now use the first derivative test to find any local min or maxes. Okay, so first derivative test, we need a sign chart to visually see how the signs are changing. Okay, so I would look at the simplest form of the first derivative, which is this, and I would try to plug in or analyze it in some way. Here on this, so like I said before, e to the x is always positive, and x plus 1 is always positive. So really, it boils down to just the x. So we can reason with that and say that this part is positive. And actually, yeah, that's also going to tell me that these two are going to be negative. Yeah, you can also just slowly piece that, like pick a number or imagine that you picked a number and reason about each of the 3 parts here, the denominator, the x, the e to the x, and you'll get this. It's fine that you actually have these 2 negatives. That basically is going to tell you that that -1 is an asymptote, which, you know, if you look it back on G, you see like, yeah, of course that's an asymptote. All right, so first derivative test tells us, let's see, local min, local max, minus to plus. So x equals 0 is a local min, and for local maxes, there are none. Okay, second derivative test. So this is the part where, you know, I'd rather finish this whole problem. I think that next time we'll have, we won't have that much time, but we will probably use most of it. So I'm just gonna maybe go a little bit over time for this calculation. So for the second derivative test, notice how this function is pretty terrible, and we're gonna need to take the derivative of this guy, which is gonna have a product rule inside of the quotient rule. So I need to take the derivative of x e to the x over x squared plus 1. So we have an x plus 1 squared times the derivative e to the x plus x e to the x minus x e to the x times the derivative of that, which is going to be 2x plus 1. And this is all over x plus 1 to the 4th power. One thing we can do is we can reduce the power just a little bit. So there's this, I can turn this into a 3. Okay. And I would prefer to actually clean this up even more. Let me, maybe I'll skip the algebra and I'll just tell you what this ends up being. So all you do is you just like, you could factor in e to the x here. You get x plus 1, which is going to combine with this, and then this just has a 2x. You can basically factor out like e to the x, and then you can combine everything to one polynomial. And with a little bit of cleaning up, you're going to end up with x squared plus 1 times e to the x on top over x plus 1 cubed. So, but remember, like the second derivative test, we're not like setting equal to 0 and solving for this guy. We're not doing a number line either. What we're doing with the second derivative test is we're plugging into the second derivative. So technically you could plug in to this first guy. It's just a little bit messy. And the thing that we need to plug in is the critical numbers that come from setting the first derivative equal to 0. So the only value we can plug in is the 0. It's not the -1. Basically, the -1 is excluded from our consideration, and it's just that the x equals 0 could be a local min or a local max, and the second derivative test will tell you which. Or it could also be inconclusive. That's when the second derivative evaluates and gives you 0. But usually you won't see that, I would say. Okay. But yeah, so we would plug in g double prime at 0. And so like, yeah, you could clearly plug that into the first guy, but I'll just plug it into the second because it's nicer. 1 times 1 divided by 1, which is greater than 0. That's the thing that matters. It's greater than 0. Therefore, concave up. So maybe I'll just go through the logic again. Concave up. Therefore, local min. Okay, so the second derivative test concludes for us that x equals 0 is a local min. I guess I should specify at x equals 0. Okay, right. So both of these tests gave us the same conclusion, and now part D is just saying which test did we prefer? Did we prefer doing the first derivative test or the second derivative test? So I think the common sense thing is to say, in this case, the first derivative test. Right. The second derivative test requires that we calculate the second derivative and then plug in. Even if we didn't do all the algebraic steps to simplify this, it's still kind of nasty to plug into this thing. Okay. Any last questions, remarks? If not, I'll see you guys next time.